Yeah, welcome back in the fourth lecture on the GNSS series. So, here we are going to talk about the Indian Regional Navigation Satellite System IRNSS, which is also known as Navigation with Indian Satellite NaviC, as the name given by the our Honorable Prime Minister. So, IRNSS is an independent regional navigation satellite system developed by ISRO with an operational name of NaviC, as we have discussed, and it is providing us the navigation facilities within India and 1500 kilometers beyond India on a 24 by 7 basis. And it also provides, in line with the other global systems and the other regional systems, two type of services for general users and for the strategic applications for the defense users. uh, The one which is used by the general user is the standard positioning service, which we get from the IRNSS receivers, and the other is the restricted service, which is for the strategic applications by the licensed receivers for that specific purpose. And it provides accuracy of better than 20 meters, and as we have tested, it is providing accuracy between 5 to 10 meters also at times when we have done the surveys. So it is providing us a good accuracy. And I have, as I have told you yesterday, already some of the mobile companies have launched the mobiles, like the Redmi Note 9 Pro, which is receiving the IRNSS L5 signal. So it is available now in the smartphones also. So the basic objectives of IRNSS are to provide reliable position, navigation, and timing service for the entire region of India and its neighborhood, with about 1500 kilometers from our national boundaries of India. And it has been designed in such a way so that the entire constellation, is visible all the time, especially by the Indian user community. As we have planned it with a limited number of satellites, so we to increase the effectiveness of it, the, the planning is done like that. And this functions totally independently from the other GNSS services, so it is fully independent in itself. Here we are using two type of orbits for the IRNSS. One is the geostationary orbit and another is the geosynchronous orbits. So we are using three satellites at three slots what we have got from the international agencies in the geostationary orbit, because geostationary slots are obtained through the international procedures. And the geosynchronous, we are putting four satellites in two orbits inclined to the equator, with inclination between 19 to 29 degree to the equator, uh, because they have been optimized for its results. So that is how we are getting these. And the IRNSS 1A, which was the first satellite of the IRNSS series, it was approximately about 125 crores, which was launched on in 2013, and the latest IRNSS 1I was launched on April 12, 2018. So IRNSS 1A has completed its life because of the problem in the satellite clock, and the current status is that we have fully operational seven IRNSS receivers in the space, orbiting in their respective orbits perfectly, providing us the terrestrial, aerial, and marine navigation services and helping us in the disaster and fleet management across the footprint, which is our entire Indian region and 1500 kilometers beyond it. So we are using here two type of services, which, as I have mentioned, the standard positioning service and the restricted positioning service, based on the two frequencies which we have received from International Communication, uh, that is the ITC, ITU, that is the International Telecommunication Union, ITU, through the Radio Conferences, WRC. So that is a platform, international platform, where we receive these uh, frequencies for the purpose of navigation. So what has been allotted to us and what we have got is L5 and S band. So we are using L5 and S band, having bandwidth of 25 megahertz and 16.5 megahertz, respectively, for our positioning services. So the IRNSS signal in space interface control document for standard positioning service version 1.1 is released in July 2019 for the public usage to provide the essential information on the IRNSS signal in space to facilitate R&D and to aid the commercial use of IRNSS signals. And the international certification has also been uh, obtained from the 3GPP platform, and that is how the IRNSS is coming now in the Qualcomm chips, 720G chip, which I have discussed yesterday, after the certification of the IRNSS signals. So the navigation data of IRNSS includes primarily the satellite ephemeris data, which gives us the coordinates of satellite at any moment, satellite clock correction parameters, satellite and signal health status, user range accuracy, and total group delay. So all these primary parameters are coming in the navigation data of IRNSS signal. Secondary navigation parameters include the satellite almanac, which includes the details of positioning of all the seven satellites in their orbits, because almanac is the entire chart, so it again takes some time to download when we operate the IRNSS receiver. As we have discussed yesterday, that GNSS receivers, when we download the almanac for downloading the data of one satellite, it takes about 30 seconds. Similarly, the secondary navigation data here provides us with the satellite almanac data of IRNSS satellites. It provides us ionospheric grid delays and confidence in it, the IRNSS time offsets with respect to the UTC and GNSS. So here also you can see that, in as in case of GPS, we follow different type of timing from International Atomic Time or the UTC. IRNSS also has an offset with the UTC and the GNSS, which is maintained by the respective IRNSS maintenance team. Then we have ionospheric delay correction coefficients, text messages, differential corrections, and earth orientation parameters. So all these things, components, are part of the IRNSS navigation data. IRNSS coverage is from 30-degree south to 50-degree north, and longitude 30-degree east to 130-degree east. So this is the primary area besides the Indian land mass which is being serviced by the IRNSS. The neighboring countries also can use IRNSS services once they have the IRNSS receivers. It is being provided by some of the vendors like the Accord software companies. They are providing the IRNSS receivers. They have miniaturized it in a dongle form also. So the miniaturization work of IRNSS has also completed. This is the front page of the ICD which I was talking about for the IRNSS, which was released recently, and I am happy to share with you, with the user community, that already these services are being provided by IRNSS, especially for the coastal regions and for helping our fishing teams, those who are involved in the fishing activities, the boatmen. They are being given warning so that they do not go out of the Indian water region. Otherwise, you know that there is a problem at times when they cross our borders, maritime borders in the Indian region. So those services are serviced by the service ID of 0111 for the high wave warning. For the cyclone warning, it is 4 times 1, and for the tsunami, it is 0011, and for normal condition, it is 1100. So the normal conditions are also represented here. So similar to the understanding of any satellite-based navigation system, either global or regional, IRNSS being regional system, to understand it again, we need to divide it into three type of segments to understand it wholly. One is the space segment, which constitutes the satellites which are launched for the purpose of IRNSS signals, providing us positioning, time, both. Then we have ground segment, which take care of the satellites, and then we have a user segment for various applications. So these are the satellites which has been launched for the purpose of IRNSS constellation, IRNS 1A to 1I, and we have completed the IRNSS constellation in 2016 March. So from March 2016 onwards, the IRNSS is fully functional. So it is already functional for over 4 years now. So it is a great accomplishment of India that we have our own regional navigation system, which is in fifth year of providing navigation. And with this year, we have seen and we will see more and more applications developing, because now in mobile we have started getting the IRNSS signal, because that will help us to create more and more Android based applications, which can be run on the fly by the users. So now IRNSS will, this year itself, I hope by the end of this year, we are going to see large number of applications in the market and the user community. So these are the some of all the details of various IRNSS satellites are always uploaded openly on the ISRO website. As I have shown you the details of GLONASS, Galileo, BEDO on their respective websites in the first lecture on the GNSS. Similarly, we also maintain the open environment that, and the details are always available for their functionality, non-functionality on the website. If a satellite is being completing its life, that information will also be shared. So we have the IRNSS 1A, which has completed now its life because of the satellite failure. Sorry, for the failure of the satellite clock. But the specifications are same for various series of IRNSS 1A satellite, and they carry two type of payloads: the navigation payload and the ranging payload. The navigation payload of IRNS satellites will transmit navigation service signals to the users. This payload will be operating in L5 band and S band. A highly accurate rubidium atomic clock is part of the navigation payload of the satellite. The ranging payload of IRNSS satellites consists of C-band transponders which facilitate accurate determination of the range of the satellite. IRNS 1A also carry corner cube retroreflectors for laser ranging, because laser ranging is one of the very accurate method of determining the position, because it works on the phase measurements. Electronically, the phase measurements can be accurate to 1% of its wavelength. So, depending upon the wavelength, it can be 1% of that. So, it provides us the very accurate. However, in India, we do not have laser ranging facility. We are currently using it from the other friendly countries, but we are in process of developing our own laser ranging facility in Tamil Nadu, which may be operational in the times to come and will provide our own backbone for the laser ranging systems. The payload specifications are Even here, the L band and S band are using right and circular polarization in horizontal, whereas C band for communication, it is using RHC and LHCP signals. Data rates are at 50 bit per second, and the modulation and access scheme is based on CDMA, because now what is happening, like L5 is there again. So L5 is a common wavelength for all the regional and global systems, so that we can use this as a part of GNSS in the resolution of the fix, that is, in the solution of the equations which provide us the xyz and the clock bias b. So L5 will is going to contribute into that. However, S band is separate, which is as of now is not being used by any of the other uh, navigation system, but it provides us with some of the unique opportunities to study the behavior of the wavelengths in L band and S band, and we are going to get certain more advantages with the S band, especially like in the ionospheric corrections, because when we are going to send the same signal on L band and S band, the difference between L band and the S band being large, we possibly will be able to do better corrections for the ionospheric region. Ionospheric region means basically when the signal travels through the ionosphere, the kind of delays it gives to the ionosphere, those should be better resolved when we are using the L5 and S band. So then, coming to the space segment, as the diagram shows, the geostationary orbit, which is in the equatorial plane, has three satellites as shown here, and in the two orbits which are inclined, when we take a basically a profile of that, they make a figure of 8, but basically it revolves around the earth, and this is the virtual path of the satellite being projected like it. So these two satellites are there in these two of the each orbits, which are in the geosynchronous orbit. That is, they have inclined orbit with respect to the equator. However, the height is same, 36,000 kilometer, keeping the same period of 24 hours. Just to recall, in case of the GPS satellites, the time period was 12 hours, where they used to have two rotations around per day. But to maximize the benefit for the, as it is, our system is a regional system, and we want our system to be visible most of the time, rather all the time, in the Indian region. So the design is like this. So the geo 3G geo stationary satellites are at 34 degree, 83 degree, and 131.5 degree east. These are the three slots. Whereas the two orbits which are inclined between 19 to 29 degree inclination, while doing the optimization exercise to benefit the signals, they cross the equator at 55 degree and 111.5 degree easting. All the IRNSS satellites have been launched through our premium launcher PSLV. The constellation was launched and completed between 2013 to 2016, and thereafter we have launched one more satellite uh, to augment it further. So currently we have fully operational seven satellites in orbit, including the one which was launched in 2018. We can say it has been able to replace 1A. We can say like that, because 1A is not functional now. And now we have a plan to launch four more satellites, making our IRNSS constellation from 7 to 11, which will provide us more redundancy in the measurements. More redundancy in the measurement means when we are doing trilateration and we are solving the equations, we can apply least square adjustment, and we can have better error reduction or error distribution. So even increasing the accuracy. So that will be the benefit. Once we launch few more satellites, the accuracy will further improve. The design considerations for constellations which are taken care are to minimize the maximum dilution of precision. The DOP we have discussed yesterday, it is a unitless number which describes the quality of the signals which we are receiving, and we have achieved the minimum satellite constellation to provide positioning in the Indian region and as per the available orbital slots in the geostationary orbit. So we are receiving the optimal DOP for the coverage region, especially the Indian landmass. We are we have designed it for full availability of 7 satellites all the time. However, you may get at times 6 also because of the constellation sometime, but most of the time we are going to get 6 to 7 satellites whenever we are operating the IRNSS receiver anywhere on the Indian landmass. So that was the space segment. Now we will come to the ground segment. So the objectives of the ground segment are to carry out housekeeping and station keeping of the IRNSS satellite. It is to carry out precise orbit determination of all IRNSS satellites using one-way, two-way, and laser ranging. Laser ranging is also a two-way type of ranging. Generally, it maintains and disseminate the IRNSS network time using an ensemble of highly stable clocks. It estimates the onboard satellite clock bias and drift rate and ionospheric delay using one-way range measurement data. It also generates ephemeris parameters that will be broadcast by IRNSS satellites for user community. And the ground segments uplink the dedicated uh, signals for the upgradation of the information on the satellites also. So these are the roles played by the ground segments at Hassan and Bhopal, so which take care of the IRNSS satellites. So this is the pictorial view of the architecture of the IRNSS ground segment. This we will discuss in detail one by one now. So the navigation control facility, that is the IRNCF, includes the IRNSS Navigation Center, that is INC, IRNSS Network Time, that is IRNWT, IRNSS CDMA Ranging Station, IRCDR, IRNSS Laser Ranging Service, ILRS, IRNSS Range and Integrity Monitoring Station, IRIMS, IRNSS Data Communication Network, IRDCN. So you can see there is a large amount of role played and responsibility which is taken care by the segment and the navigation control facility. Then we have IRNSS satellite control facility. So IRNSS TTC, that is telemetry tracking command center, and the land uplink station INLUS, and the IRNSS satellite control center IRNSS CC. Okay, so these two constitute INLUS and IRSCC. They constitute the IRNSS satellite control facility. Will The next is the IRNSS navigation control center. What is the role of it? So it estimates and predict ephemeris data, that is the coordinates of the IRNSS satellites. It calculates the correction for satellite vehicle clock and maintain IRNSS time, which is a very complex job. As I have discussed yesterday, that for the GPS they maintain about 200 atomic clocks and other type of clocks globally, and create an ensembled clock to give one time. In case of IRNS also, it is not one clock, but it is many clocks are there, and the clocks are having an ensembled modeling to produce one unique time, which is provided to the satellites and for to the IRNSS receivers to maintain highly accurate time, because we need a very high accurate time of the order of 1 in 10 to the power 14 to 1 in 10 to the power 15. So that accuracy is maintained by these ensembled clocks. The INC also determine the unnecessary corrections, and it again determines the integrity. So integrity is again the trust. Finally, what you are getting the coordinates, how much you can rely on that. So that integrity has to be maintained, and it is taken care by INC. The INC also transmit the clock and ephemeris corrections to the telemetry tracking and command stations for uplinking of the satellites. Coming to IRNWT, the IRNSS time is derived from an ensembled clock, as I have told, which combines cesium clocks and active hydrogen measure clocks. Then IRNWT is the reference for all type of corrections being computed for each of the spacecraft. This is the architecture of IRNSS showing its configuration. So we have the uplink station here for telemetry tracking and command. We have CDMA ranging, IREMS, user base on the ground, in the air, and it can be in the ocean also, in the within the within the footprint of the IRNSS. So this is the IRNSS timing center, INC, and laser ranging stations which we are using from abroad. Then IRNSS ground segment includes IRCDR, which is the CDMA ranging center. So we are using code division multiple access codes for the ranging, that is the measurement of the distance between the satellite and the antenna for the INSS receiver. So it facilitates accurate ranging of INSS satellites. Then same thing is done by the laser ranging station. The INSS ranging and integrity monitoring stations receive the data from the seven satellites in the geostationary orbit and geosynchronous orbit, and they transmit the data to the navigation control center. They facilitate one-way ranging of the seven satellites from their respective orbits. Coming to the IRNSS data communication link, that is the IRDCN. The IRDCN provide a data communication network connecting the entire system with link level redundancy, equipment level redundancy, and changeover strategies for fail-safe mode. So a lot of redundancy is being used here so that the if there is a kind of a breakage in the signal transmission or the information transmission to the control center, it switch over to other option. So there are multiple levels of redundancy which has been provided. In case of first failure, it switches to the second level, and in case of second failure also it switches to the third level. So multiple level redundancy is provided in the IRDCN so that the communication link never fails, or the discontinuity should not happen at any moment of time. Then coming to IRNSS TTC and land uplink stations, they receive the telemetry from the IRNSS constellation. They telecommand the IRNSS constellation, and they uplink the navigation updates. So any of software updates can be maintained through INLS facility. The satellite control center manages and maintain the entire satellite constellation. So they do their role to look after all the satellites and their health parameters. They maintain the orbit maneuvering for keeping the satellite in their respective orbits. So this is a very important job which is taken care by the these command centers. Then the navigation center for IRNSS is located in the Deep Space Network Complex of Indian Space Research Organization at Belalu, which you might have heard, which has been taken care of our Chandrayaan mission also. So at the same center we have facility for IRNSS also. The navigation center is functioning as the main ground station for the satellite system. This is also responsible for the time reference, generation of navigation messages, and monitoring and control of the ground facilities, including ranging stations. So it is one kind of a headquarter for IRNSS activities. So the SPS receivers, that is a standard positioning service receivers of IRNSS, they can be of following types. The single frequency receivers can either function in L5 band IRNSS user receiver or can function as S band IRNSS user receiver. Whereas the dual frequency will receive L5 and S band IRNSS user receive signals both. So that is how the IRNSS receivers can also be single frequency or dual frequency for the standard positioning service. Whereas for the restricted services, the receivers are of dual frequency, that is, they receive L5 and the S band both. Why? Because as we have discussed yesterday, the ionospheric errors in ranging may have an error of the order of 5 meter to 50 meter when the satellite rises above the horizon to the position it comes just above the zenith, that is the position above the satellite. The errors may increase from 5 to 50 meters. These errors in the ionospheric delay can only be corrected if we are using a dual frequency receiver, so that these delays can be calculated when the same signal is passing through and there is a delay between the two signals reaching the receiver via two wavelengths, carrier waves at L5 and S band. So to have this correction of ionospheric errors, we need to have dual frequency receivers. Then we can have combined IRNSS and SNPs, other satellite navigation systems. So we can have combined IRNSS and other. Basically, it will be a GNSS receiver where IRNSS is also part of it. So the smartphones which I was talking about, they are basically providing us this combined IRNSS and SNP facility currently, with the rider that they are providing L5 signal only, not the S band signal. So L5 signal is available in the smartphone now using the Qualcomm chip along with the GPS and GLONASS signals. So they are providing this option. So the this is a diagram showing the where the overlap regions of the various signals being used by various satellite constellations for the purpose of satellite navigation launched by US, Russia, European Union, and India. So those things are plotted on this diagram.
Yeah, good afternoon to all of you. Now, as you have already listened about these two navigation systems from Indian side, like IRNSS and S-bar system, that is Gagan. So Gagan is the augmentation system, whereas IRNSS is a independent navigation system. I think you might have been, you are very much aware of it, of these two types of systems from Indian Space Research Organization, Gagan and IRNSS. Gagan means augmentation system, whereas IRNSS means a independent navigation system, means it helps us to locate our positions. So we will cover some few more points, like I will be covering about the case studies which we have carried out at Indian Institute of Remote Sensing. And there is one more case study which was done for the government of India also. These two or three case studies I will be covering during this lecture. So before going to that case studies, the slide which shows over here is the goal of GNSS civil interoperability. So now it is very much clear from this slide that if now all of you are aware that in order to know the position using a GPS receiver, at least 4 satellites are required. They need to be visible in the sky to calculate the position at a particular place from that receiver. Now I can have the 4 satellites from IRNSS. I can have the 4 satellites from GPS, Galileo, or any system. I can have the 4 satellites which gives me the position. Now this interoperability over here, it means that this is a very interesting feature here. I can have the signals not only from a particular system. We can have from different systems I can have those 4 satellites to calculate my position. It means I can have one signal from GPS, 2 signals from IRNSS, one from Galileo, then also my position will be calculated. So whichever satellites are available in the sky at that particular of time, the position will be calculated based upon those signals received from those satellites. It is not necessarily that there is only one satellite. As you can see from this picture over here also, this person is trying to get his position. Now all these systems are available in the sky. Now whichever 4 satellite gives the best results, based upon those only his positions will be calculated. So this kind of system this system is known as interoperability. Means I am getting signals for the position calculations not only from one system, from varied systems, from different systems I can have it. And now this has as is visible from the slide also, where the ideal interoperability, it allows navigation with one signal each from 4 or more systems with no additional receiver cost or complexity. I need not to have any additional receiver or any additional complexity to get my position calculated. So our IRNSS also falls into the same category. It is quite interoperable with other navigation systems. I can have my position calculated from anything. So interoperable, it means better together than separate. The tagline for interoperable is like this only. So I can have it calculated from different kinds of systems also. So if we talk about Gagan and IRNSS, they are the two independent systems here which are being offered by Indian Space Research Organization. So Gagan is as already I had told to you, that is an augmentation system. It augments or it corrects your position or the positions which we are receiving from the GPS signals. So once to be very simple in terms, I will say कि I have one receiver that is getting the signals from the GPS satellite systems or the Navstar satellite system. Now there may be some inaccuracies due to some ionospheric or the atmospheric conditions. Now accuracies may be there. So now this Gagan, what it does, it removes those inaccuracies and further augments the accuracy of the position. It improves the accuracy of those signals. How it does it? Now this Gagan system, it has one reference system, Indian reference system, IRNRES. It also has master control centers and it has Indian land uplink stations. So these 3 systems, INRES, that is a reference station, control station and the uplink. Reference stations, they are calculating all the atmospheric and ionospheric conditions with them. Now once those conditions are calculated or observed, they are sent to the master control center. From master control center, all the corrections are done and these corrections are sent to the uplink station. From the uplink stations, these systems goes directly to the satellite, and from the satellite I get the corrected signals in my receiver. That has been done with the help of this Gagan system. So now ISRO has set up around 15 reference stations across India with collaboration Airport Authority of India. Along with them, around 15 reference stations which have been spread across the country. So now these ground stations, they are the ground stations which are calculating all those atmospheric and ionospheric conditions. So now based on these conditions, they act as a correction factors from those GPS signals. Now Gagan uses the Gagan's user segment consists of SBAS receiver capable of receiving GPS signals and corrections from the geostationary satellite. Now at the user end, this my receiver should be capable of getting those SBAS signals or the signals from the Gagan. It should be capable of getting those signals from the Gagan system. Okay, once it is done, then those corrections are applied to it and my positional accuracy is improved. Now the same thing is written over here, the last bullet also here. Data from this is transmitted, as I told you earlier also, data from reference station is transmitted to the control station. In the control station it is processed and then it is sent to the uplink system, and uplink system send it to the geostationary satellite, and from geostationary satellite my receiver receives those signals with an accuracy of this 3 meter. So it varies at various places, it can vary, but it has been observed that it gives you accuracy in the order of 3 meter horizontal and 4 meter vertical. So over a large number of studies has been done, and this kind of accuracies have been achieved with the help of these kind of systems. Independently, if you go with the GPS systems, so you get the accuracy of, let us say, around 10 meter or 15 meters. But if you add this Gagan system into it, your accuracy is improved to the order of 3 meter or 4 meter vertical. So it is helping for the precise location calculation using this Gagan system. Okay. Next, now these are the reference stations, where these reference stations are located all over the India. You can see it here. It is covering the entire Indian continent, Indian subcontinent. These are the places where all these reference stations have been located, and here somewhere here we have our control facilities, control center also, and we have our uplink center also. Here reference stations, they are across the country. Now since now suppose I want to calculate the position at this place, so now this reference station, it will be having all the correction parameters pertaining to this area. Okay, now this area, because at different part of the country we have different atmospheric and atmospheric conditions, so they are calculated by these reference stations, and accordingly they are uploaded to the satellites, and from there we get it. Location specific accuracies also we are getting into our receivers. Next, if we go, this was the basic about the Gagan system. Now let us talk something about the applications of IRNSS and or NaviC system. What are the various applications that can be done with the help of these navigation systems, the regional navigation system. Okay, so the first one, if we talk about, that is the terrestrial, aerial and maritime navigation. So any type of navigation, whether it be a land or it can be in the air or it can be in the water, that can be done with the help of our IRNSS systems. Similarly, it is also useful for the disaster management. Any kind of response, or a person, you want to connect to that person, or he want to send some information about his location information, at which places that person has been stranded. So all these are some of the applications where this NaviC system can be utilized during the disaster scenario. I will show you one case study also where we have used Gagan system for this kind of, for the disaster management. One example is there with me in the coming slides that I will be covering. So similarly, for the natural resources management, where these natural resources are located on the surface of earth, so that location information for this natural resource management can also be carried out with the help of these kind of system. Now another example is vehicle tracking and fleet management. So having covered about this natural resource management, we can also do the tracking of the vehicles or the fleet management, where that fleet is going. A continuous monitoring of the entire fleet can be monitored with the help of this system. Now similarly, integration with the mobile phones. This system can also be integrated with the mobile phones. Currently may not be available, but slowly and slowly it is coming into the market, and soon we have this NaviC system also in the mobile phones. And currently we have some Bluetooth receivers are also there from the NaviC. So directly I can connect, one small Bluetooth receiver is there. Through that I can connect my mobile and I can get my location information from NaviC systems also. Okay, it also helps us in providing the precise timing. In the mapping, surveying and geodetic data capture is also possible with the help of NaviC system. Now again, if you see here, terrestrial navigation aid for the hikers and the travelers. So it also helps these kinds of applications, like if people are traveling somewhere or some hikers are there, so they also provide this location information to these in these kinds of applications. Now visual and voice navigation for the drivers can also be is one more application area of NaviC. Now if you see, if we go into the scientific research, so atmospheric studies, crystal movement or the crystal deformations, these are some of the applications or some of the scientific applications which can be carried out with our NaviC systems as well. These are some new case studies or the new studies that are being carried out all over in the entire globe. So NaviC system fits into that kind of research applications as well. So similarly, we have business solutions and many more applications are there. We can think of which are applications we can perform with the help of NaviC system. This some of the applications are listed over here. So any application you can think of, and you can also start using this system in these kinds of applications. So how we have conducted, or some studies we have carried out, or some case studies that we had carried out, that I will try to show in the few slides here. Like if you see it here, we try to do one small accuracy assessment of the NaviC receiver. Ki how accurate these receivers are coming to us. Now how to calculate that accuracy? So we had some long time reference stations, means some stations where the position information was known. I was having some one particular place where I had a 90 days or 90 hour 90 or around 2-3 months observations was collected at that place, and its position was calculated. That was a known position actually, from for which the locations are known with high accuracy. We went with our NaviC receiver to that place itself, from where the location is known. Okay, at that place we took around 1 hour observation, and now if you see it, during that 1 hour, at every second one signal is coming from the satellites. For one position information is coming from those satellites. So this kind of pattern was observed over there. It is not like it will fall exactly at that place only. It varies. Actually, it will never come. It may be in some millimeters or in very small units where this information is captured here. Now, if you see this kind of pattern we are getting it, it is very, you can say, a very round kind of signal over here. So only some variation is there in the y direction over here. Otherwise, it is going to that particular place only. So using this, we got this was the receiver which we had used it at that time. This is that antenna for that IRNSS receiver. Now this was the receiver over there. Then we required one battery also over here, and one laptop where the software where these locations can be logged, or the location information of 1 hour locations were being logged. So all those locations were logged in this laptop system. But currently we have now this entire system has been miniaturized. So all these things goes into one small unit also, where I can capture those locations. Now if you see it here, another IRNSS NaviC or the GPS GLONASS receivers here, it provides the high performance fast TTF, IRNSS, GPS, GLONASS, Gagan receivers are there. Some parameters are displayed over here. So these all are this some of the properties of those Gagan receivers here. Ki how many channels are there? 40 channels are over there. Active antenna port for interface to GNSS antenna. So similarly, we have these kinds of properties for that NaviC receiver or the Gagan receiver. Now if you see it here, now this IRNSS receiver is coming in like this kind of symbols also. I have one dongle which I can directly plug into my laptop or any USB device, and then get those location in my and get those signals from IRNSS or the NaviC into my device. Now it is miniaturized to this Bluetooth receiver also here. You just take this Bluetooth receiver along with you, and you have a mobile phone along with you, and this is a separate receiver only. You connect your Bluetooth NaviC receiver, and that signals will be available in your mobile phones also. So this small study has also been carried out here, in which we have taken these signals from this Bluetooth receiver, and we have carried out some asset management, inventory or the asset management kind of studies using this dongle receiver. So if we talk about the accuracy assessment which we had got it, the study was carried out in around June 2016. So this was the sky plot of those IRNSS NaviC satellites here. If you see it here, the RMSE and the positional and the height accuracy, so it was around 3.5 meter positional accuracy we were able to get it, and the height information was around 3.1 accurate with the accuracy of this much unit we were able to get it here. Now this is one the screen show you that the display of those how the satellites were the sky plot we will say the graphical user interface, yeah, graphical interface user interface of the software. Now if you see it here, this software is able to show not only the IRNSS but it has SBAS satellites also are there, and GPS satellites are also there. So the integrated software is there which allows to visualize where these satellites are located and from where I am getting my position being calculated from these satellites. As I told you earlier also, I can have a mix of GPS and IRNSS also and get my position calculated. So that was an interoperable system. So earlier the case study was at a particular place. Ki what is accuracy we are getting at that place. Second case study was like ki how much accuracy we get while tracking from one place to another. Now we tracked along with the this NaviC receiver from let us say from Dehradun to this Masuri, and another track was from Dehradun up to this Gaurikund. So now here if you see it, the variation in the terrain also here. Now if we go from Dehradun to Masuri, that is the elevation difference of around 1000 meters, whereas the distance is around 40 kilometers. Similarly from Dehradun to Gaurikund, the distance may be around 250 or 300 kilometers, and elevation is again 1000 or 1500-meter difference only. So now but here in this path we had this there were deep valleys were there along the river also. The GPS that this NaviC receiver was carried along with us, whereas in case of Masuri we have steep bends are there, like hairpin bend kinds of things. So we wanted to calculate what is the accuracy we are getting in these kind of sharp bends or deep valleys. So these are the two different scenarios here, two different kinds of terrain where we tested the NaviC receivers. I will play one video here which will show me how the signals were. Now here we had carried not only the NaviC but also the Gagan receiver along with us for these kinds of tracks. So just I will play one track. You can visualize it how the track was calculated or it was observed there. Okay, so one video if I try to play here, if you see it here, this is one Rishikesh to Devrayag. So if you see this yellow line over here, now this yellow line was the track and this is along the road. If we see it more closely, so we were able to get it perfectly over that road only, how the Gagan signal we were able to receive along this road. So most of the time, most of means we were able to get almost 100%. We were able to get it on the road itself. The signals never went away from the road. It was along the road only. With if you see it here, little bit of variation is there. That may be due to some steep valleys and all those things. But more or less, our signals were along that road only. You can visualize this kind of terrain was there while moving from from Rishikesh to the Devrayag area. If you see it, the road, the pattern of the road, it was perfectly captured by the Gagan receivers here. No variation over here. If you see it, all along it is going along the road, and it is along the road only. So this was the data that we captured. We were able to get it from that Gagan receiver. So based upon that, based upon these results, we were able to see yes, these signals are very much accurately giving the locational information. And if you see it here, how it was going upside, and sometimes now from here it was going uphill, and then it went all along to this side over here, and here some landslide and all those things were there, and we were able to capture this kind of things. The road is like this only over here. Okay, so if you see it here, it is going all along, and this was the road itself here. So all the signals are along that road only. So similar kind of result we got while traveling from Dehradun to Masuri also. There we have more complex road system is there. Like some sharp bends are there, and those bends are not one, two. There may be many bends are there. On all those bands, which we were able to get this kind of accuracy here. Now this satellite data is also ortho rectified. We have got the satellite data from one of our geo portal, that is Bhuvan Geo portal. Sometime we will be having one lecture on that Bhuvan Geo portal also. On top of it, we had this overlaid this satellite data, this Gagan signals over here. So this was one small example that I wanted to show you how much accurately we are able to get those signals from these satellites. If you see it here, now here it is showing the signals not only from one, from the other uh, systems also. Like here if you see the Gagan system signals, we are getting it from the GPS also and from IRNSS. From all the three receivers we had with that, this exercise was only to calculate the accuracy of these kinds of systems here. If we talk another application, I will tell you now. This was the accuracy assessment. Now this is the disaster management one application which we carried out in 2013. Like at that time there was one disaster in Kedarnath. All of you may be aware of it. So after that, government of India approached us to assess the damage that was caused in these areas. So again, in that we had made use of one mobile app. Now this mobile app, along with this mobile app, we had one Gagan receiver also along with us. So we were able to capture the location from the Gagan receiver, highly accurate location we wanted for it. Actually, at which place, how many, if you see it here, what was the objective of this one? It was development of an appropriate tool for field data collection through crowdsourcing and integration with the Bhuvan Geo portal. So this was one major objective where this Gagan receivers were utilized for this kind of application. Let us say for this if you say input towards formulating guidelines for restoration and development activities. So this kind of activities was the end use of this application here. They want to do some restoration activities, but in order to do the restoration activities, I need to assess how much damage has occurred, assessment of those damage. So this was carried out with the help of this mobile app. So there was damage to the buildings and damage to the infrastructure, damage to the roads, bridges, culverts, other infrastructure, landslide, road bank, river bank erosion. So these were the different kind of damages that were assessed or they were captured using our mobile application. So now this mobile, we will say like it was able to get the location of these damaged areas, and some information also was fed into that mobile location information, location information through Gagan receiver or the and along with the GPS also, and some information gathered by seeing those sites or by taking some interview from the local people over there and capturing the photograph of that location also. So that all was integrated, and this mobile app was developed, and it was very much successful. And now it was not only one person, there were different organizations involved into it, like IRS was there, NRSC was the major role which played over there. Then Survey of India was also there, DST, HNB Gadwal University, Kumaon Universities, and Wadia Institute of Himalayan Geology. So these all organizations were met, they put their effort together for this kind of solutions for using this mobile app, where this Gagan or the navigation system or the navigation observations were utilized for damage assessment. If you see some screenshot of that mobile app here, now here building or the field data collection was there. Now send already collected data. If you see it here, the mobile app was capable of capturing the location information, line and polygon also. So these locations were captured and they were directly sent to the Bhuvan Geo portal over there. If you see here one screenshot, how many points were able to collect. This one, if you see it here, all those points, those were captured with that mobile app along with the Gagan receiver. These were mapped on this Bhuvan Geo portal, and we were able to appraise how much damage has been caused in that area due to that flash flood. So this was around one case study for the damage assessment also. Similarly, we can do any number of like asset management or asset inventory of the asset. If you want to do, like suppose you have one organization and we want to do the monitoring as well as data collection for all the assets, that also can be integrated with your NaviC or the Gagan receivers. They will capture those locations. You collect other information along with them, and they can be combined together along with some other multimedia information, and then that can be sent directly from that mobile app to the central server, from where it can be managed or analyzed for further decision making. So there are n number of applications which can be utilized for which we can think of using this Gagan or the any kind of navigation systems. So with this, I end it. I hope I am able to appraise you about some of the applications of this NaviC and the Gagan receivers. Thank you very much.